Good afternoon, students. This is our first lecture of the Modeling and Simulation of Dynamical Systems course. This course primarily deals with the analysis of the response and the behavior of physical systems that we encounter in electrical, mechanical, and mechatronics engineering. So in this introductory lecture, I'm going to talk about the course outline and the course textbooks and recommended books. And I would also give you an overview of different types of systems that we're going to study. And we are going to discuss the basic ideas which are the foundation of this course, such as the idea of modeling and the concept of simulation with the help of an examples. So basically, we'll be discussing how to model mechanical systems, electrical systems, as well as electromechanical systems. And then in the latter half of this course, we are going to talk about the hydraulics systems as well as the pneumatic systems, and the course will conclude with the thermal systems. And there will be a recurrent theme of this course in which we're going to discuss modeling and simulation based upon transfer function models as well as the state space models. So basically these are two different ways to model and also to simulate the physical systems. And in your lab sessions, we are going to describe and discuss various methods of simulations of all these types of systems that I have just described. We are going to follow the textbook Modeling and Simulation of Dynamical Systems by Robert L. Woods, Kent L. Lawrence. See if you can find the latest version, latest edition of this book. You're also encouraged to consult the reference books. Those are primarily based upon the course of control engineering that you will take in the next semester. So some handy reference books include Modern Control Engineering by Ogata and also by Norman S. Nice. So the textbook and the reference books will be your best way to prepare for this course throughout this semester. The grading policy will be follows. As far as your theory part is concerned, we're going to have 5 different assessments, including quiz 1, quiz 2, midterm exam, and the final exam, with the corresponding weights shown here. But there is also something important that weighs into your assessment, the final part, that is the project of this course. And this project will be about modeling and simulating the ankle foot prosthesis. It is closely related to one of our milestone projects in the human-centered robotics lab. So the details of this project will be revealed in the future lectures. The lab grading policy, again, we have assessments based upon the lab evaluation as well as a lab project, and bulk of the weight will be that of the lab evaluations. And then as we talked about the project in case of the theory grade, we also have the project for the lab as well. But remember, it is the same project which is going to count towards your lab grade. It counts about 20% of the grade. And the simulation part of the project will be determining 20% of your lab grade. So essentially the project will have 2 components: the theory part, which is about modeling, that is going to count towards the 20% of your theory grade, and the simulation part will determine 20% of your lab grade. All right then, so the first question, why should one study modeling and simulation? So I'll give you an example of real life systems. Real life systems, as you know, can be very complex. Some of them are more complex or more complicated than the others. But let's take an extreme example of a very complicated system, such as building a space shuttle that is destined to land on the surface of the Mars. So these kind of space shuttles are regularly designed and manufactured by NASA, obviously in association with other companies and other organizations. And that begs an important question: how complex is your space shuttle? So based upon the information that I gathered from the NASA website, a single space shuttle may consist up to 2.5 million different components or parts. And these include wires, electrical wiring, can be as long as 370 kilometers. And it also contains more than 1,000 valves, 1,400 circuit breakers, and 25,000 insulating tiles. So already you can see that it's a complicated electromechanical as well as thermal systems because we're talking about the mechanical components, we're talking about valves, we're talking about electrical components as well as thermal components such as insulating tiles. And then the space shuttle must meet certain requirements, such as we need this shuttle to be able to accelerate from rest up to 28,000 kilometers per hour in about less than somewhere around 8.5 minutes. So it has to accelerate very fast, and it has to survive some very high temperatures, extreme temperatures, I beg your pardon. So it should be able to survive something less than 150 Celsius and some temperature in excess of 1600 Celsius. So because the stakes are very high, and well, we saw in the last slide where we said that it was $1 billion question. How can you design a reliable space shuttle that is expected to meet certain specific requirements? And one thing for sure is that you just cannot start building space shuttle without having the design verification, right? So whatever design of a space shuttle NASA has in its mind, the first step it must go through or at some point must go through what we call as the design verification. So what do we mean by design verification? Essentially, it means that we must be able to use some kind of our engineering knowledge to describe how each one of those 2.5 million components would work in the proposed design. And that essentially constitutes the modeling step of the design verification. So the way we describe the functionality of the individual component constitutes the modeling steps. And in the next part of the design verification, once we have put together those components on a piece of a paper, obviously putting 2.5 million components on a piece of a paper will be difficult, but let's say you want to put together in some ways in your imagination, or more likely in a computer program, right? It's much easier to model things in a computer program. So that brings us to our next point. You would like to evaluate how those parts are put together to perform some useful function. And if those functional requirements are adequately met, some of those were discussed in the last slide. So writing a computer program to see if those 2.5 million components would work together as required, and evaluating their combined functionality describes the simulation. And it is quite clear that in the modern digital age, we have very powerful systems which are capable of performing computational intensive simulations. So Once the design step is complete and we have the models of each one of those million components, then we would like to see if those million components can work together to meet the design requirements. And that's why once modeling and simulation uh, verify the design, then we can either proceed to the further design refinement, or we can just proceed to building the space shuttle. So this example shows why or how modeling and simulation play an important role in building real-life complex systems, which integrate electrical, mechanical, hydraulic, and or thermal subsystems. Now, at this point, an important differentiation that needs to be made is the difference between the static system and the dynamic system. So we call system to be dynamic if its output depends upon the past output. And if the system output does not depend upon the past output, it is called static system. Static system is also known as the memoryless system. So one thing which is implied in this definition is that one can expect system output to be dependent on the current input. That is fairly obvious. But what is not so obvious is the dependency on the past output. What makes a system dynamic is essentially the memory element. And throughout this course, we are going to explore the memory aspect of the system, the properties of the dynamic system from different perspectives. Very often we will talk about the order of the system, which is basically derived by the number of memory elements in the dynamic system. Schematically, one can define static system as a system in which the output depends only on the current input or the input at the present time. So in terms of the signals and system representation here, this u of t is the input to the system and y of t is the output, and we say that y of t is some function of the input u of t. In case of multi-input system where the inputs are u1, u2 up to um, then the output will be derived by the function of all these inputs. Now note the indices within the parentheses. All these indices are t, which is representing the time at given instant. So the output at time t depends on the inputs at time t. It has no dependency on the past outputs. So in that sense, the systems under consideration here are basically the static systems. And there are several examples of static systems in our real life. If we take an example of a static electrical system, we have a voltage, or it can also be a current source, connected to a network of resistances. So in this case, we have three resistances, R1, R2, and R3. And the output of the system is taken as the voltage across the resistance R3. And if you apply the voltage divider rule, or you can solve the circuit by using Kirchhoff's current law or the voltage law, whichever law is applied here, you can see that the output voltage depends upon the input voltage or the current. We haven't really specified what exactly u of t is, but the output at time t only depends upon the input at time t multiplied by some constant number that is determined by the values of the resistances. So a simple electrical network of resistances is a good example of a static system. There can also be examples of static systems which are non-electrical by nature. So for example, we talk about furnitures, bridges, buildings, and if we look at their characteristics without their vibration analysis, then these are all examples of mechanical static systems. What about dynamical systems or dynamic system? So we said before that the system is dynamic if the current output may depend on the past history of the output as well as the present value of the input variables. So essentially, we say that the output y of t is some function of the input at time tau, where tau is a time which is less than or equal to t and obviously greater than or equal to 0. We cannot have time which is negative in this case. So essentially this range of tau is describing the past history. So note also that this u is again used as the input to the system. So a good example of a dynamical system is a moving mass. So if a block of a mass experiences some input force, so the input u in this example will be force and the output is taken as displacement. To relate input force with the output displacement, we can utilize Newton's second law of motion, where we say that the force equals mass times acceleration. And therefore we have the formula where force mu or u is equal to mass times acceleration. Now this double derivative of y is an acceleration, and the reason is that if y is the displacement, then rate of change of displacement, which is essentially the first derivative of y, becomes velocity, and then another rate of change will convert velocity into acceleration. So double derivative of displacement is essentially the rate of change of displacement, which is essentially rate of change of velocity. That means acceleration. So one thing to note over here is that in case of dynamical or dynamic system, we often deal with these derivatives. In this case, we are dealing with the double derivatives. For notational consistency, it is reminded that in this course and also in the future courses on control systems, you will find mu of t or u of t denoting the input to the system, as opposed to denoting the step function that we have been using in the calculus classes or somewhere else. So with this notation, I would like you to keep this, keep the use of this notation, that is the u of t or mu of t will be used to denote the input. Now input can be other than the step function. It can be a sinusoidal function. It can be an impulse function that we are going to talk about later on. One can talk about several real-life dynamic systems. In case of electrical systems, the simplest dynamic system that we can construct is the RC circuit. So we have a voltage source connected to a network containing resistance and capacitance in series, where the output is the voltage across the capacitor and the input is the voltage of the voltage source. If we talk about mechanical system, then we can talk about a car. It is a rather complicated dynamic system where you can say that you have a drag force PV which is acting on the car to the left, and then there is a throttle which is forcing the car move towards the right, moving or make it move forward. So the two inputs. And then what about the dynamical properties of the car? Well, we may be interested in the speed of the car or the velocity or the acceleration. Um, this can also be modeled as mass spring and damper system. So we are going to spend quite a lot of time modeling and simulating the mass spring or the mechanical system containing mass spring and or damper. But a very basic example of a dynamical system is a pendulum. It's something that we're all familiar with, and pendulum can be considered as an example of a dynamical system where input is a displacement and output can be taken either as the velocity or the acceleration of the ball connected to an inextensible string. So what defines a model? Model represents simplified representation or abstraction of reality. In other words, a model represents the engineer's view of the physical system. But this begs an important question, that why simplicity is needed? Because the reality of the physical system is generally too complex to copy exactly. And very often, much of the complexity is not needed or becomes irrelevant in the actual problem solving situation. So it's a simplified view of the world or the physical system that defines the model. It means that model represents the conception or the concept of the physical system that we develop in our minds to solve the problem. What different types of models are used in mechatronics and other branches of engineering? It turns out that there are three different types of models that engineers can work with. The first of them is the physical model, then the mathematical model, and the third type is the computer model. And what are the examples? In case of a physical model, it might be one of the course projects that you develop in the course of mechanisms. For example, you may have developed a rack and pinion hardware, which is a good approximation of the car steering system. Note that the physical model in this case represents a physical hardware. A mathematical model describes a system of mathematical equations that can be solved easily or analytically. One good example might be the Newton's law of cooling, which requires us to solve just first order differential equation. The third type of model is a computer model. In computer model, we deal with the mathematical equations, but these are just too complex to solve manually. Thus, we need a computer program to solve these equations. A good example of a computer model is a computer program that calculates the lowest energy state of some molecule. So where does the discussion of modeling and simulation fit into the study of the system? We are given a system, and one way to study the system or to analyze the behavior of the system or to evaluate its performance is to perform actual experiments on the system, collect data, and then process or analyze data. The other way is to work with the model of the system. So in this case, we don't deal with the actual system, rather we deal with the model of the system. And as we saw in the previous slide, there can be multiple types of model. Two of them are used here for the further discussion. One of them is the physical model, which actually means a simplified version of the system that describes the essential functionality of the system to a reasonable extent. And then we have a mathematical model, which might be be a which might be a model uh, of model described by a system of equations that can be solved easily analytically or by using a computer program. Usually, we like to deal with the mathematical model because that eliminates the need of building a physical system, no matter how simple the system is. Rather, we want to invest our effort on the software side. And in the modern digital age, when we have lots of powerful computing facilities, it makes a lot of sense to invest in the mathematical models and to perform simulation. Obviously, there might be some simpler systems whose dynamics could be described by the analytical solution, but uh, here along this downward arrow, we are talking about simulation, where we deal with rather complex systems which have practical significance. And there can be several different types of simulations. We can talk about the simulation in the time domain, describing the time domain behavior of the system. We can do the frequency domain simulation of the system, in which we analyze the response of the system when the inputs are changing frequencies. And we can talk about a hybrid domain, time and frequency both. And there are some other variants of that as well. So what different types of mathematical models do we have, and why they're so useful? First of all, like we said earlier, that mathematical models can be used in connection with the high performance computing system to simulate rather complex physical systems which have practical significance. And they can be used in prediction and forecasting, prognostics, diagnostics, design and performance evaluation, and control system design. And throughout the course, we are going to look at several examples where the mathematical model can be very useful. Further classification of the mathematical models can be made at different levels. For instance, whether the model is linear or non-linear, or either it is deterministic or probabilistic, is it static and dynamic or dynamic? And we have already seen the difference between the two. The discrete versus continuous, or white box, black box, and gray box. Some of these differences are relevant to our future study, the topics that we are going to cover in this course. Some of them are rather irrelevant. So we would primarily focus on the linear mathematical models, and we are going to limit ourselves to the discussion of deterministic models. Very often we will be interested in analyzing dynamic systems, continuous systems, and last but not least, here we are going to explore essentially the white box and the gray box. But what exactly do we mean by the box representation that is going to be described in the next slide? The first type is the black box model. Now, black box model is the simplest model where we deal only with the input and the output of the system. And we don't wish to deal with the internal dynamics of the system because they're either too complex or they're unknown or difficult to model. So the black box model is easy to model because it only requires us to relate input with the output. Let's take a look at an example of a heat radiating system. Uh, some of these systems I have seen in the West, in United Kingdom and United States. And the idea here is that we wish to control the temperature of the room by adjusting this knob, and this determines the amount of heat radiated by the structure. So the input to the system might be considered as the rotation of this knob or the position of this knob, and the output might be the temperature. So if you make a graph between the position of the valve or the knob and the corresponding room temperature, an example graph might look like this, as shown by the dots. The graph here plots the temperature against the valve position. In this case, the valve position is the input and the temperature is the output. Now, because we don't wish to deal with the internal dynamics of the system, all we care about is to relate input, that is X, with the output Y. This can be achieved easily with the help of curve fitting problem, for example. Just find the best possible curve that connects all these data points or adequately pass through all these points. And in this case, we have chosen the second order polynomial, and a computer program has computed for us the coefficient of the polynomial. So note that in case of a black box model, the only thing we care about is the relationship between the input and the output, and it doesn't tell us anything about the internal dynamics or the internal characteristics of the system. The next type is the gray box model. Now in this case, we know the input and the output, but we also have some information about the internal dynamics of the system. So an example will be helpful to clarify the difference between the gray box model and the black box model. So example here is that if we know the number of energy storing components of the system, and in the next slide we're going to look at an example of a thermal systems where the number of heat storing elements is known as the number of thermal capacitances in the thermal systems. So if the number of energy storing elements are known, but their values are unknown, so that will be an example of a gray box model. Now, in contrast with the black box model, here we don't even know the number of energy storing elements. A typical application of a gray box modeling is in connection with the system identification task. And it was actually the modeling and simulation semester project that was given last year, where the system response was given to the students, and they were also informed of the number of energy storing elements. And the project was about identify the system by calculating the values of the energy storing elements. So for instance, if we are given that the order means the number of energy storing elements of the system is 2, which the system in this case is again the heat radiating systems, but now we're also given an additional piece of information that there are 2 energy storing elements, so we can write down the dynamical equation of the system, which obviously we are going to learn in a few weeks time. But right now, suppose that we come up with this differential equation, a second order differential equation that corresponds to the number of energy storing elements, which we're saying there are 2, that's given, for example. Then the coefficients of each one of these derivative term, a2, a1, and a0, well, a0 is without derivative, and b is the coefficient of the input. Those are unknown. So calculating those values will be part of the gray box modeling. And note that y here represents temperature and the input is the valve position. And lastly, we have the white box model. Here, the inputs, outputs are known, as well as the details of the internal dynamics of the systems. So for example, we know exactly how many energy storing elements in the systems, what is the order of the differential equation. In fact, what exactly is the differential equation that relates the output with the input. And notice also that the coefficient values which were unknown in the gray box model, they're also given here. So for example, 3 and -1. So this white box models is the most elaborated model, but then that requires us to have a significantly complete knowledge of the system so that we can proceed with the white box modeling. Although in many real-life applications, this is not generally the case. So let us summarize some of the basic rules of mathematical modeling, because that is primarily what this course is all about. So a mathematical model of a real-world system is derived from the combination of physical laws and the experimental means. So physical laws will determine the model structure, whether the system needs to be modeled using a linear or a non-linear system, and how many energy storing elements, which primarily defines the order of the system. Again, all of this discussion will come later. Then what are the parameters of the models? For instance, the parameter may refer to the coefficients of the differential equations, and how can they be validated experimentally. And the mathematical model of the dynamical systems can often be expressed as differential equation, discrete time or continuous time differential. Well, in case of discrete time, it will be a difference equation. So difference or differential equation are going to be used to describe the dynamics of the system in case of mathematical modeling. System models, there are different ways. So we have seen the differential equation can be used. There are other ways to represent systems dynamics. One type that we are going to study very soon is known as the state space representation, and we also deal with the transfer function that reduces the representation to the input and the output variables. So we're going to deal with all three types of these system modeling representation, describing various electrical, mechanical, and electromechanical systems. How would you approach a design problem in which you're required to design and therefore later on develop the dynamic system? First of all, you have to define the system and its components, then formulate the mathematical model and the list of necessary assumptions. Write the differential equations describing the model, or the state space equations, or the transfer function. And then you need to solve these equations for the desired output variables. You need to examine the solution and, if necessary, reanalyze and redesign the system. So what do we mean by simulation? You may have heard of this word before. It is about executing the model on a digital computer. This is a modern definition of the simulation, and the purpose of the simulation is to analyze the execution output. So essentially, simulation is a principle of learning by doing. That is, we need to learn about the system. We must first build a model of some sort and then operate the model. So one thing that we should note this at this stage is that simulation precedes modeling. So you need to have a model first, and then only then you can execute the model. An interesting example for some of you might be that of using electrical or electronic circuit simulators such as Proteus, where you first design an electrical or electronic circuit, and before you, and assuming that the circuit is too complex, and you first wish to verify that your circuit will work when you implement that on the breadboard or in the hardware PCB. So what you're going to do is that you're first going to test that circuit in the software using simulation. And if you look at the simulator, the circuit simulator, it has models of different components. So circuit simulator contains model of hundreds of different electrical and electronic components such as resistances, capacitances, inductors, and semiconductor devices such as diodes and transistors. And when you construct a circuit from these basic components, you construct a model of the circuit essentially, and then you give it to a computer program when you click on the run button so that it simulates. So running the circuit in the software is essentially simulating. And what your computer does is that it solves a set of differential equations. And after solving those differential equations with different initial conditions and constraints, it gives you an output. And from there, you can learn if your circuit is giving you the desired output or not. So as you can see that simulation can be advantageous. So what are some of the advantages to simulations? Well, it can be used to study existing systems without disrupting the ongoing operations. And the main advantage to me lies in testing before committing the resources. So we looked at an example of designing the space shuttle or designing the complex electrical circuit. So you wish to test your design before you commit resources or before you go ahead and fabricate or construct or to implement that in the hardware. It allows us to control time, and it allows us to gain insight into which variables are important from the system performance viewpoint. So alongside, we also have some disadvantages to simulation. Part of the problem is that building a simulation has a prerequisite, which is that we have a model, or we know how to build a model, which itself is an art as well as science. It's a non-trivial task to build a quality model, and the credibility of the analysis greatly depends upon the model or the skill of a person who models a physical system. There can be many unknowns that unknown attributes of the system that may remain unmodeled, and they are crucial to describe system performance. Sometimes simulation results are difficult to interpret, and simulation analysis can take time, and it can be resource intensive. It may need intensive computational resources. Therefore, in summary, we would advise that one should not choose simulation when we have an easier or a path of a lesser resistance and a path that gives us the insight into the system dynamics by using analytical methods, because that is going to be more efficient and productive and going to give us quicker results. All right, so with that, I would like to formally conclude our first lecture on modeling and simulation course. I hope all of you enjoyed the lecture, and I also expect students to have lots of questions in their mind regarding this subject and the topics that we are going to cover. For that, there is going to be a question and answer session, but that is going to be held next week. So till that time, stay safe and goodbye. Thank you.